This is my submission for homework chapter 28 exam. Part A states, how much current must a long straight wire carry in order for the magnetic field that it produces 1.40 centimeters from the central axis of the wire to have a magnitude of 3.20 times 10 to the negative 5t. So for this, we're going to use the formula B is equal to mu of 0 times I divided by 2 pi divided by R. And then we're going to solve for I because that's what we're being asked. So this is equal to B times 2 pi divided by mu. And then this is equal to 3.20 times 10 to the negative 5th that we are given times 2 pi times 1.4 times 10 to the negative 2, which we're given, divided by 4 pi times 10 to the negative 7. And then this is equal to 1.6 times 1.4, which is equal to 2.24a. Part B states, two long, straight conducting wires are both perpendicular to the xy plane. Wire 1 passes through the point x equals 0, y equals 1 centimeter, z equals 0, and carries a current 1a. So I'm gonna write that down. Y is equal to 1 centimeter, c equals 0, and 1a. In the positive c direction, wire 2 passes through the point x equals 0, y equals negative 1 centimeters, c equals 0, and carries a current of 4a, also in the positive z direction. Find the net magnetic field due to both wires at x equals 0, y equals 0, and z equals 0. So for this, we're going to also use the same formula that we previously used. Mu equals 0 times I divided by 2 pi times R. But we're going to be distinguishing these by using 1s and 2s. So this would be I1, R1. So B1 is equal to 4 pi times 10 to the negative 7 times 1 for A divided by 2 pi times 1 times 10 to the negative 2. So this is, the vector is positive I. So for B2, this is equal to, same thing, mu of 0 times I, but in this case 2, divided by 2 pi R2. And then this is equal to 4 pi times 10 to the negative 7 divided by 2 pi times 1 times 10 to the negative 2. Whoops. And our vector will also be a positive I. So our B net, in order to get this B net, we need to add B1 and B2. So here, I'm gonna make some space over here. This would be equal to 4 pi times 10 to the negative 7 divided by 2 pi times 1 times 10 to the negative 2, parentheses multiplied, parentheses 1 minus 4, and our positive I vector. And this is equal to, let's see, 4 pi. This will be negative. First of all, 4 pi times 10 to the negative 7 divided by 2 pi times 1 times 10 to the negative 2. This is 3a positive I vector, and this is equal to negative 6 times 10 to the negative 5t positive I vector. So they're asking us for it, like for the 3 coordinates basically. So since this is our x, our answers would be negative 6 times 10 to the negative 5, comma 0, comma 0. In part C, we're asked to find the net magnetic field due to both wires at x equals 0, y equals 2 centimeters, and z equals 0. So x equals 0, y equals 2 centimeters, z equals 0. Oops, I almost wrote it. 0. So for this, once again, same formula. B of 1 is equal to mu of 0 times 1, I of 1 divided by 2 pi r1. This is equal to 4 pi times 10 to the negative 7 times 1a divided by 2 pi times 1 times 10 to the negative 2, and this is a negative I vector. We're going to find B2, which is equal to mu of 0, I of 2, 2 pi, R of 2. This is equal to 4 pi times 10 to the negative 7 times 4a divided by 2 pi times 3 times 10 to the negative 2, negative I vector again. Let's remember that our B net is B1 plus B2. And then this is equal to 4 pi times 10 to the negative 7 divided by 2 pi times 1 times 10 to the negative 2, 4 over 3 plus 1 negative I vector. And then this is equal to negative 4.67 times 10 to the negative 5t I vector. And since we're being asked for coordinates, since this is I, this would be our x. So negative 0.67 times 10 to the negative 5, comma 0, comma 0. Okay, D is asking us to find the net magnetic field due to both wires at x equals 0, y equals negative 2 centimeters, and z equals 0. So x equals 0, y equals negative 2 centimeters, z equals 0. So same formula. B1 is equal to mu of 0, I equals 1, I of 1 divided by 2 pi r1. This is equal to 4 times 4 pi. 4 pi times 10 to the negative 7 times 1a divided by 2 pi times 1 times 10 to the negative 2. B2 is equal to mu of 0, I of 2 divided by 2 pi R of 2. Just gonna make some space here. Let me think. Okay, so this would be 4 pi times 10 to the negative 7 times 4a divided by 2 pi times 3 times 10 to the negative 2. Once again, b net is equal to b1 plus b2. And then this is equal to 4 pi times 10 to the negative 7. And this will be multiplied by, I will say in just a second, this is divided by 2 pi times 1 times 10 to the negative 2. And then this is all going to be multiplied by 1 over 3 plus 4 positive I vector. And this is equal to 8.67 times 10 to the negative 5t positive I vector. So since this is our x, our y would be 0, or z would be 0. Okay. Part E. A long, straight conducting wire carries a current of 2 amperes. 2A. A second identical wire is parallel to the first and separated from it by 4 centimeters. The magnetic field at a point halfway between the two wires has magnitude of 6 times 10 to the negative 5t. What is the current in the second wire if its direction isn't the same as in the first wire? So we remember that B net is equal to B1 plus B2. So here we're going to use same formula that we previously used, mu 0 divided by 4 pi. We're going to rearrange this a little different for this problem just to make it easier to solve. So this will be multiplied by 2 divided by r, and then I2 minus IR. This is actually a different formula now that I'm thinking about it. Not the same as the one that we used before, but very similar. So we are now just going to plug our values in. So it would be 6 times 10 to the negative 5 is equal to 4 pi times 10 to the negative 7 divided by 2 pi times 0.02 times 2 minus I of 2. And then I of 2 is equal to 8 amperes. Okay, part F. What is the current in the second wire if its direction is opposite to that in the first wire? So we're basically going to use the same setup. So 6 times 10 to the negative 5 power is equal to 4 pi times 10 to the negative 7 divided by 2 pi times 0.02. Ow, my finger hurts. Times 2 plus I of 2, and then I of 2 would be equal to 4a. Part G is asking us, sorry that I'm writing weird, it's just my pinky is like strained. I've been writing all day. 2 straight, parallel, and superconducting wires are 0.900 meters apart. Both wires are oriented straight up and down. One wire carries a current of 1.30 times 10 to the 4th power, A, upward, and experiences a magnetic force per unit length of 95 newtons per meter that attracts it to the other wire. What are the magnitude of the current in the other wire? That is written weird, but anyways, this we're going to solve with this following formula. F divided by L is equal to mu at 0, I of 1 times I of 2 divided by 2 pi times the distance. So plugging in the values that were given, this would be equal to 95 is equal to 4 pi times 10 to the negative 7 times 1.3 times 10 to the 4th power times I of 2, which we don't know about, divided by 2 pi times 0.9. And then I of 2 is equal to 95. We're just rearranging this. 95 times 2 pi times 0.9 divided by 2 pi times 10 to the negative 7 power times 1.3 times 10 to the 4th power. And all of this is equal to 3.29 times 10 to the 4th power A. And last but not least, part H is asking us what is the direction of the current in the other wire. So because the wires attract to each other, their currents must be going in the same direction, right? So that means that they will be going in the same direction, and this same direction happens to be upward. So that is the answer for part H. So again, this is Victoria Atencio, and this is my submission for exam chapter 28. Thank you.